Okay, so welcome everybody to today's sustainability seminar with Dr. Tomasz Kozlowski. My name is Emily Gusky, and I'm a community engagement and outreach specialist at the Illinois Sustainable Technology Center, which is a part of the Prairie Research Institute at the University of Illinois Urbana-Champaign. Today, we would like to start the seminar with the university's land acknowledgement. As a land-grant institution, the University of Illinois at Urbana-Champaign has a responsibility to acknowledge the historical context in which it exists. In order to remind ourselves and our community, we will begin this event with the following statement. We are currently on the lands of the Peoria, Kaskaskia, Piankashaw, Weah, Miami, Mascoutin, Odawa, Sauk, Meskwaki, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. It is necessary for us to acknowledge these Native nations and for us to work with them as we move forward as an institution. Over the next 150 years, we will be a vibrant community inclusive of all of our differences with Native peoples at the core of our efforts. We'd also like to note that all Illinois Sustainable Technology Center seminars are certified green events through the University of Illinois Institute for Sustainability, Energy, and Environment. To find out more about certified green events through the university, please visit sustainability.illinois.edu. If you would like to find out more about ISTC's seminar series or sign up for the events email list, please visit istc.illinois.edu/events. A couple of housekeeping items. Today's seminar is being recorded. It's also a hybrid session, so you will see we have some participants in the room as well as online. The recording will be available within about a week. Everyone online, please remain muted, and everybody in the room also please keep your cell phones on mute as well. We'll be taking questions at the end of the seminar. If you're in the room, you can just raise your hand and ask, and the microphone will pick it up. If you're online, we would ask that you put the question in the chat, and then we will be reading that out loud to our speaker. If you're having any technical difficulties, please send me a private chat message and we will work through that together. So to introduce our speaker today is Dr. Tomasz Kozlowski, who will be presenting on microreactors enabling new markets for nuclear power. Tomasz is a professor at the University of Illinois Urbana-Champaign. He received his PhD in nuclear engineering from Purdue University in 2005, where he worked on spatial homogenization methods for transport calculation, multi-physics coupling, and Parks code development. He also worked at the Division of Nuclear Power Safety at the Royal Institute of Technology in Stockholm, Sweden, where he taught numerical methods and conducted research on BWR stability, safety analysis, and multi-physics coupling methods for deterministic safety analysis. At the University of Illinois, he works on BWR spent fuel criticality safety, BWR instability, high order numerical methods for two-phase flow, uncertainty quantification of system codes, multi-physics uncertainty and multi-physics coupling, PWR, MSR load follow analysis, computational statistics, and Bayesian inverse. Welcome, Tomasz.
Thank you. Welcome, everybody. Tomasz Kozlowski. I'm here, a professor in nuclear engineering, or in nuclear plasma engineering, and today I'll talk about microreactor project that we have here at the University of Illinois. I know some of you know about it, some of you don't. Then welcome, let's find out. I'd like to start with this. There'll be a couple of slides that are some basic nuclear physics or nuclear energy concept. So I assume everybody's seen this, EMC squared. And it actually, you can convince yourself it's true. The biggest source of nuclear power on Earth is sun, and it's the biggest source in the universe. And it's a proton-proton cycle. So 4 hydrogen become helium. And if you remember from chemistry or physics, molar masses of elements, you can look up 4 hydrogens and 1 helium, and you can see 1, if you multiply by 4, and 300 grams per mole is definitely more than 4 and 3,000 grams per mole. You can convince yourself with your chemistry or physics and molar masses. So moving on to nuclear power or fission. So here's one of the fission reactions, and you can look up the molar masses of all the uranium, neutron, barium, plutonium, and other neutrons. I will just sum it up for you. And again, this you can look up in chemistry and physics the molar masses. It's 336 grams per mole, it's 335 grams per mole. Loss of mass, become energy. Great. So now what about this? If you do burning of coal or carbohydrate or anything else, you'll look up carbon is 12 grams per mole, oxygen 32, and CO2 is 42 grams per mole. So what's going on? Is there mass loss or no mass loss? Anybody thinks mass loss? Anybody thinks no mass loss? Everybody in quantum state of mass loss and no mass loss. Not quantum state is not allowed. Either mass loss or no mass loss. Observe it. Observe yourself. No mass loss? Good. Then the follow-up question should be, is this always true or sometimes true? This has to be always true. This has to be, if this is always true, then what's going on here? The problem is that it's such a small mass loss, it's practically unmeasurable. You would have to go to 7, 8, 9 decimal place. You cannot do this. If you see 43.99999999999, you just say 34, or sorry, 44, right? It's okay. So there is tiny mass loss, but it's so tiny it's unmeasurable, or practically unmeasurable. And that's the benefit of nuclear power, is that this is definitely noticeable. Fraction of it's what is it? 0.8 of a mole is grams per mole lost versus 1 billion or whatever that is, or trillion of grams per mole. Good. So let me start with the UIUC team that works on the microreactor project. Caleb Brooks is the lead. Tim Granville is the associate director. I'm one of the researchers. These are the professors in NPRE and other people in NPRE and outside of NPRE involved in the project, plus a number of graduate students, and there were undergraduate students, and there have been also a few more graduate or undergraduate students. Actually, as far as undergraduate students, it was a very large population that worked on it at different times for different specific purposes. So we have a very good team: licensing specialists, technical specialists like myself, and my colleagues, experiments, reactor design. We have all people from FNS. So we have team that wants to see this to completion. Project team: the University of Illinois will be the owner and operator of the proposed reactor. Ultra-safe nuclear, USNC, is the technology vendor, meaning that they provide the reactor, MMR, modular microreactor. Industry partners: NPR, AECOM, and BGS. NPR is a specialist in safety analysis of experimental and commercial reactors. AECOM is the environmental safety, and BGS is different large capital projects. Many different government and private projects. And finally, Morgan Lewis is a legal company that specializes in nuclear law. Now, what I want to cover in this presentation is 3 topics. First, what is microreactor and how is it different? Then, nuclear projects 101, big picture and why campus, and then specifically why university campus makes sense and why University of Illinois is the right place out of all the campuses. And then what is the Illinois microreactor demonstration project? So first, this is the slide out of Washington Post, or sorry, not slide, a picture out of Washington Post that shows this, which is the total energy use and the fraction of fossil fuels versus clean electricity. And this pale yellow is the nuclear, and this darker yellow is other. So mostly wind or solar. And if you see, people are shocked that out of clean energy, vast majority of Illinois is the nuclear power. If that nuclear power was to disappear, guess who we would become as? Go down, 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 down. We would become just like Indiana. Not that Indiana is a bad state, but perhaps we should not aspire to mirror Indiana. But yeah, just remove nuclear part. This is where you are. You are in the, we become from this to this, the very bottom of the fraction of clean versus fossil fuels. energy for the state. So then, perhaps some of you seen this kind of thing about, people involved in nuclear know very well about the different generations of nuclear reactors. The Gen 1, we usually think about the early experiments and prototypes. Gen 2, that's the current PWR that are operating in the US. And Gen 3 and 3 plus, these are the advanced commercial power plants that are being built around the world. Not in the US specifically, but definitely, I guess Vogel would be the one that started this year, would be the exception, would be the Gen 3 plus that was built in the US. But there's many of them around the world, but right in the US, everything is here. We want to go over and go all the way to revolutionary advanced reactors. So to illustrate it in a more in other demonstrated this kind of progress relative to another technology, think about cell phones. Just like first vision in 42, the first cell phone, it was radio, not cellular, but it worked, radio phone in the 40s. Then first cell phone was were in 70s, looked like this. Now imagine these people suddenly getting this. Or imagine you getting this. How would you feel if all of our phones disappeared and we had to use this? I've never seen this. I've only seen this on like the original Miami Vice, and I've seen it on Saved by the Bell. So I never had the pleasure of seeing this live and even using. But perhaps some of you, anybody used it? I assume many people see it in real life, and some of you used it in person. Yeah. So now, this is just 30, 40 years. And again, many of you used it, but still, you're going from this to something very different. So what is microreactor technology? On the fundamental level, it's a nuclear reactor that's just smaller. First, how small? Typically, we categorize it as a power up to 20 megawatts. That power is a little fuzzy. So there's definitely concepts that are 30 megawatts that are microreactors, and smaller 10 megawatts microreactors. So this is not a hard limit. I'll come back to that in a minute. Long core life up to 20 years, and similar in size. So this is actually 20, 30 megawatts is similar to research and test reactors, which there is about 25 in the US research and test reactors. This limit, if you want to go by this, why is this limit meaningful, or why is this limit kind of set at this level? The reactor vessel has to be small enough to fit on a track rail regularly. So it's road. The largest component is road transportable. That's the big thing. So that immediately limits to something like I don't know, what's the diameter, like 12 or 13 feet diameter, whatever is I cannot think right now what it is, but the largest track that's road transportable. The other benefit is reduce on-site construction. You need plug and play. All of these are, because they are small enough, they can be constructed in a factory, right? You don't need a large capital project on site, building for years. Everything can be factory assembled and tested, which allows for simple and more responsive design concepts. If something has to be adjusted, you can do it in factory. Not once you have years of construction, they are designed to be inherently safe. I'll come back to it later. And if you follow the nuclear news, there is dozens of startup companies that have competing designs in sodium type, light water type, gas type, heat pipe type. I don't know if there's lead, nothing new, but there are like in the world also lead concepts. So let's go back to comparison of nuclear power, traditional versus microreactor, with our other heavy industries. So on a very global level, there are four basic categories of how to think about heavy industry: the unit size, factory fabrications, licensing or testing, and higher term product. And unfortunately, in case of current nuclear, large reactors, you are on the bad side of all four categories. The unit size is large, or is better. Factory fabrication, no. Licensing or testing, depending on the industry, it's long. Higher term product, no. You want to pay for electrons more than a cent per kilowatt? Probably not. And probably you think they should be even lower. So we don't value electrons that much. Usually it's like few cents per kilowatt, which is a lot of power for very, very little money. Whereas on the other hand, with microreactors, we try to flip all these four categories into the positive. Unit size, small. Far prefabricated, yes. Licensing, probably not short, but shorter and high return product. As long as you don't rely on electrons, which are actually cheap, we can get it into high value product, which I'll talk about a little later. Now, the next need is the nuclear workforce. So these are actually two axes. The line, the blue line, is this axis. That's the number of research, and it says university, but it's really research and test reactors in US. So you see the peak was around 50 in the late 70s. There was one built, one addition in 92, and then since then everything just goes down. Now it's about 25. And again, it's not only university. There's other test reactors that are not on university campuses, but most of them are university campuses. When you talk about the solid bar is the number of bachelor, master, PhD students in nuclear engineering programs. You see the peak was around 80, the bar around 2000. I graduated in 2000. My graduating class of 5. My graduating class in bachelor was class of 5. When I think about it, crazy. Imagine the department that has 5 students in as a senior year. Yeah, what would the university think of that? Yeah, probably not good. That's why there was a good reason why the number of research reactors went down. But now we're back to to the high average, historical average. But still, number of research reactors did not go up. So as the new reactors, either light water or microreactors, are built, the need for experimental reactor will go up. The need for the workforce will go up. There's no way around. Now, if I said that electrons are not that highly valued, what is that we need that for? What is the research that we need to do? And what is the advancement that is needed for advanced reactors, microreactors, and advanced reactors is a category of advanced reactor that we need to overcome. These are actually all the things that are not related to electricity production. So new safeguards and security practices. This has to be small and are kind of co-located in a either densely populated or co-located with other industrial processes that are not electricity production. Integrated energy systems, since we imagine the future where it will be many smaller dispersed energy sources. Instrumentation of control for smaller systems. Operations that are not now large baseload power, but perhaps more load following, perhaps more intermittent as the solar and wind goes up and down. There needs to be something else that can compensate, go down when there is high wind and solar, and then compensate when there's low winds. And educational training, which I mentioned from the last one, this needs to recover to something about 50 in a long term for sure. And these are all the things where either microreactor our experimental reactor can contribute to, or where microreactors can contribute to as once deployed commercially. And I'll come back to these issues. I come back to this later when we talk about Illinois demonstration project. Now, what's really needed, part of what the need is a market demonstration. Everybody is afraid to be the first one. And, there are good reasons for it. But I'll say, give analogy to electric cars. When Tesla came out, many people were reluctant. Who was the first one that bought it? There were people who bought it, but are you now less reluctant to buy an electric car than you were a few years ago? I would imagine so. I don't have one, but at least I'm not reluctant to buy one, to be the first, few hundred to do it. And there are particular circumstances where the microreactors fit very well. And these circumstances are microgrids, embedded grids, small communities. We are not remote community, but we fit this very well. We have our own grid, we have our own embedded grid, small community, few thousand people. For thermal power, there is a combined heat and power application. For large light water reactor, it makes no economic sense. But for a small reactor, will be not without waste heat, into the atmosphere or the lake, but actually use it for district heating. So that's okay, there it is, district heating. Energy intensive processes, not in our case, but again, for industrial, that makes a lot of sense. And process, so again, so that would be for industrial process. And finally, for resilience and reliability, critical infrastructure, backup power data centers. Maybe you've seen recent news in this year, not next year, that many large IT companies are looking for microreactors, small modular reactors for their computing needs. Now, when you talk, this is also very region specific. If you look at Illinois, this is the price at the end of 22 and the yearly increase in residential, commercial, industrial, and also an average from end of 2011 to end of 22. Sorry, 2021 to 2020, 1 increase. So we know, so and US total is about 10%. But someplace, imagine that your bill goes up 25%, 30%, 30% in 1 year. And it's the industrial processes that are the heavy user, not the residential, right? So in a market where it's not, the electricity is not around 10, 20 cents per kilowatt hours, but 40 and going up rapidly, once you get to 50 cents per kilowatt hour, then this becomes competitive. So now, big picture, what do you need and why university campus and University of Illinois makes sense? So you need reaction site, technology, license, fuel insurance, and public engagement. So for reactor site, why university campus? We specifically have all university campuses with nuclear programs have a long legacy of guarding nuclear engineering, and especially in Illinois. I'll talk about it later. We have large energy users for steam, chilled electricity, and chilled water. We have very, diverse needs, not just electricity. We have diverse experience across all relevant areas of science and engineering. So whether construction, whether manufacturing, whether concrete technology, I talked about manufacturing. Reactor design, also radiation protection. We have everything covered within the university in one campus. We have very ambitious carbon reduction goals. And we have infrastructure to meet world permits. So definitely, nuclear engineering can expand. Other clean energy programs within environmental engineering, within ISTC can expand to accommodate more workforce for clean energy futures. Why microreactor? So now why microreactor makes sense for university reactor? It's similar size to existing university reactors. So actually, university or research reactors do start at like fraction of megawatt, almost no power, all the way to 20, 30 megawatts. So like MIT reactor, MSTC, Missouri, NIST reactor, they are like 20, 30 megawatt range. So they actually produce this much energy and they already exist. Small site footprint. You can look up our old trigger, I'll talk about it later. Those larger those are larger research reactors, they already exist in population centers. They are already, you can look at MIT, it's already next to Radiological. It's already next to other university buildings. And our trigger reactor was, next to Loomis and Loomis and MNTL, not MNTL. And what's the material testing? I forget again. Anyway, the material testing building. License. So this gets a little more technical. So if you see, maybe you've seen on the news something like Part 52, Part 50, Part 52, Part 53 license. That is for commercial power plants. That is not what we have, what we're doing. For experimental, there are two paths, 104C or 105, and we're going for 104 license. And again, if you follow nuclear law, then that's meaningful. I imagine that for you it's not meaningful, but it's basically experimental license, not the commercial, which is different path. It's prototype friendly, so all those experimental reactors actually vast majority of them are unique and purpose designed for specific purpose, unique. Fast path to demonstration under NRC rules. They are intended, their intention is of the license to promote research, development, and demonstration to optimize future commercial deployment. So actually, this is the important part of this license is actually optimize future commercial deployment. That's the purpose of this license. And as a US university, we are fee exempt. The fuel, where does one get the fuel? Again, the benefit of US university is that DOE has RTR program, well now it's called University Fuel Services Program, where DOE, Department of Energy, does provide the fuel, not for ownership, as a lease. That means that DOE takes it away. So I mentioned that US now has about 25 experimental reactors. Where do you think fuel comes from? All of them get it from DOE. Where does it go to? The commercial power plant, commercial side has a problem, but DOE takes all the fuel, and they are stored in Idaho, Savannah Riverside, perhaps also Los Alamos. So there are fuel storage for experimental reactors. All those that I mentioned, the biggest one, Missouri reactor, MIT reactor, NIST reactor, high Fermi no bridge, they are refueled. Some of them are refueled 2 times per year. So the fuel already travels around the US, both fresh fuel and the spent fuel travels around the US constantly. People usually don't know about it, but yeah, these reactors are refueled. Our would not be refueled ever, but these experimental reactors are refueled, some of them a few times a year. Yeah, so it's decent payback. Insurance. So the benefit of US university or state university that we already have state insurance have a unique insurance model compared to commercial nuclear reactor. So our insurance will be covered the same as the trigger as the past campus nuclear reactor. And finally, public engagements. Here is a billboard. I'll read it. I engineered a totally safe design for nuclear power plants. How sure are you that it is safe? 100%. Just keep it away from big town. It was an engineering problem after all, right? So in the end, all roads will go through public perception. So we want to show that it's a completely safe technology, that it will be co-located next to other facilities. I'll show potential site or proposed site by us, that it's next to our sports facilities and next to parking lots. And again, some buildings will be taken over by the facility, but there's campus all around. So, getting into the Illinois Microreactor Demonstration Project. The mission statement is that Illinois Microreactor Demonstration Project mission is to de-risk advanced reactor deployment and enable new paradigm of nuclear power for education, research, and scale demonstration. I'll get to that point a little later. But basically, if you think about university and a large industrial project like starting doing large demonstration project like a nuclear reactor, there are 2 core missions of university. On one side, education, training, and engagement. So we can already train engineers and scientists. We can educate in the public. We can do operator training. We can do installation maintenance. The other core mission is research and development. So we can do reactor and component testing or optimization and research on critical enabling technologies and other synergistic applications that I talked about earlier. But as a cross-cutting mission, so what brings it together is actually this at-scale demonstration. This is what's needed for the future of advanced reactors. Electricity production, district heat production, hydrogen production, integrated thermal storage, and other high-value processes. In that case, we're talking about things like ammonia production. That probably would not be us, but something like ammonia production, something like heat for like what's it called, like a steel mill or metallurgy process, these kind of things. Although again, that would not be part of our project. So for advanced reactors, these are the challenges that have to be overcome for them to be adopted worldwide. Sorry, not worldwide, or on a large scale, commercial scale. Cybersecurity. The traditional reactors are all analog operated. They could be completely disconnected from the network. The future reactors would not be able to. Sensors. So everything is in traditional reactors is analog. The new reactors will be digital. That's another R&D area. Maintenance. Since they are smaller, that's a good thing, but they also operate longer, much longer, meaning that maintenance requirements will be different. And finally, operations. The large reactors are intended as a baseload power. This probably would not be intended as a baseload power. Therefore, operating schemes would be different. And finally, at-scale demonstration of integration with adjacent facilities. With hydrogen production, with fertilizer production, district heating, and again, hydrogen for transportation. Okay. So critical path, where the project stands and what is next. The UIC USNC partnership started, I don't know, 2020 maybe. Early terms of conditions, supporting team, decision alignment, licensing application. So this part of this 104C application is that construction license is separate. So CP stands for construction permit. You need preliminary PSAR, preliminary safety analysis report, and ER environmental report. That is to be allowed to start construction. That does not mean you can operate yet. The separate is OL, operating license, that requires FSAR final safety analysis report. And again, these are terms that are specific to this 104C license. We expect submission of PSAR and environmental report by the end of 2024, and submission of FSAR at the end of 2 years later in 2026, and then operation, in 2 or 3 years later. So this is, the current, that's where we are. The future would be fuel production, procurement and fabrication, site preparation, construction, and final operation. So that is, past PSAR. So this is up to PSAR and operating license. That's that's it. Now, I started about Illinois and UIUC legacy. Is that 42, the first sustained chain reaction that happened here, outside of Chicago, right? The University of Chicago. The first, there were many first reactors depending on the category, but the first that operated, that was intended to be operational as experimental reactor, 46. I don't even know where the argument is. Then 59, Morrisville, first full commercial nuclear power plant, fully commercial, fully private. And perhaps we had Trigger that operated, Trigger reactor that operated with 38 years with with no incidents, no events, no controversies, thousands of public visitors. It was actually 6,000 megawatt transient. This is crazy. It could pulse to 6,000 megawatts. It could generate as much power as a large commercial power plant for millisecond, but it did. It's true. And then 1 megawatt steady state power shut down in '98, and now it's kind of north of Loomis. What is the material? I don't know. I forget the name of the building. So it's a green parking lot for the building the reactors to be. People working on top, people working on the side while the reactor is operating. That's completely safe and completely doable. So where we are between Champaign, Urbana, and Savoy. Here's some statistics. I won't go through it. You probably know. But basically the gray area, the grayish, is the relatively densely populated area. Now zooming in just on the, so this was about 10 miles by 10 miles. Now when you zoom in on the 1.5 by 1.5 just the campus, this is the main quad, the GE quad, the university, the union, and this is where the trigger was. So this is green and this is Goodwin. So this is the Loomis building, and then this is material building, and there was trigger that was operating for 38 years with no problem. Where we are proposing the new microreactor is next to Abbott. I'll show it on the next slide. So perhaps you recognize this. This is Oak Street. This is the north direction. Abbott, actual picture, geological survey. There is a basketball court. There is a personal services building. This is on actually the university plans to remove this building, or relocate personal services building somewhere, department somewhere else. These are existing coolers for the Abbott parking lot. So this is the proposed site. And again, this is north, south, west, east, and the railroad track, and the New Street. Same layout. This is approximate. So geological survey would be taken as an administrative or experimental building. The nuclear reactor would be, would take part of this existing parking lot between the building and the coolers. and the steam plant and the molten salt storage somewhere in between. And again, this is like a conceptual layout, not the detail. We could actually have the final layout of the reactor and the other equipment. The nice thing about University of Illinois that it actually has about 55 megawatt average electricity demand and about 60 megawatt thermal demand. There is some, when you think about our energy need campus, there is some from Ameren, some from Abbott, some from chilled water system. We envision the microreactor is envisioned to be connected to Abbott and provide steam or high temperature to Abbott for the other processes, for electricity, for district heating, for driving turbines for the chilled water systems. Right. In addition, there is wind and solar. So since they are, you see this is 1 year period for the I think electricity, 1 year for blue waters, 1 year blue waters, 1 year for I don't know what this is. This is the gasoline usage by the campus and by the Urbana-Champaign metro transit system, and this is wind and solar. It's very intermittent, so other things have to compensate for it. Technology overview. So this brownish is actually graphite. That is this part. This black is also graphite. This assembly block is about 2 feet high by 2 feet wide. These pellets are about this size, so about inch high and about half-inch thick, like a end of a thumb. Instead of each pellet is a micro spheres about the size of a grain, which actually contain the fuel. So that's how the whole core is. And so this is the whole core is here. This for the scale, this is like a normal story of a building. So this is 1 story, 2 story, and this is like actually 2 stories combined. So again, this block is about 2 feet high, 1 foot wide, put together in this hexagonal pattern. The brown is also graphite. So it has to be reflected from the side and from the top and bottom of the graphite. That's a very standard and very easy material. So the primary system, the coolant is helium at 3 megapascals, inlet 300 Celsius, outlet 360. So that's the maximum temperature that could be provided. The secondary side is molten salt. So that's called solar salt. Solar salt you can look up. It's a standard salt, sodium potassium salt nitride that is used in actually by solar thermal plants. Solar plants can be photovoltaic, but solar plants they're also thermal. They generate heat right with the reflector lamps. So this is used very standard product, solar salt, potassium and sodium chloride used already at these temperature ranges for the solar thermal plants. The safety is to retain hot fission products, store negative feedbacks, and put it to natural forces, meaning that once the reactor is or the circulation is off, but the reactor is still hot, the natural circulation of helium through the core is already enough to cool it. I'll come back to that point in a minute. So people, rightfully so, ask a lot about safety. There is 2 main safety conceptually, 2 safety mechanisms in size, in small size, and in fuel form. So why is it important? First, safety in size. The fundamental difference of nuclear power versus other power sources is that if you turn off the coal or oil power plant, turn off the flame, the vessel, the boiler is still hot, but there's no way for it to get hotter. There's no energy source. It can be red hot, fine, but it will not get hotter. There's no way. The nuclear power plant, people, with Chernobyl was, let's say, I would say a different category, but between Fukushima and Three Mile, the reactor was off. Effectively, there was little fission or negligible fission. Is the decay heat. There is still decay of radioactive products that does generate energy. There's no way around it. But the nice thing is that this decay heat is just a fraction, a known fraction, about 6% of the initial power. So now, in terms of 3,000 megawatt reactor, 5-6% power is 180. After 100 seconds, 100 megawatts. After 1 day, it's 50 megawatts. You still have to pull 50 megawatts of power. But if your nominal power is 200 times smaller, then after 1 day, that is the same ratio, 200 times lower, it's about 1/10 of megawatt. So anybody has a Honda Civic, or at least Honda Civic? Are you afraid of Honda Civic melting? Anybody afraid of Honda Civic melting? Why not? Of your engine melting. I mean, you're driving, blowing air on it. It generates a lot of power. Guess how much power it generates? You can look up 130 horsepower. That's 1/10 megawatt. This is equivalent power of a 130 horsepower engine. So there are smaller and bigger sizes, but the normal, the standard Honda Civic is a 130 or 140 horsepower engine. That's it. Okay, that's after 1 day. So that's why such power, yes, you can pull just by blowing air on it, just like if you pull your car, with blowing air. The second fuel form, silicon carbide. Anybody heard of Moore's hardness scale? One person. What's the hardest thing? Diamond, scale of 10. Guess what's right below it? Silicon carbide. Another question. What do you think melts faster? What do you think melts easier? Lava or silicon carbide? Lava. The earth melts faster than silicon carbide. A lot faster. Okay? So this is one of the strongest material that we have, silicon carbide, and one of the most heat resistant. And the kernel, this is about this 0.8, so it's like automatic pencil. They're about either 0.5 or 0.7 millimeters. So inside is a uranium sphere covered by carbon, covered by silicon carbide, and covered by carbon. And again, there are reasons why it should be carbon, but there's also ferrocarbon carbide. So now imagine like a grain of sand made out of diamond. How would you crush it? It's basically impossible. In the end, if you really try, is there a way? Perhaps. In the end, we do manufacture diamonds somehow, like the ring somehow, but it's not an easy process. So this is silicon carbide, radical, the carbons on the board scale, radical that. So the vision statement, that's the same. I think it's a great time to be a nuclear engineer. Small reactors have potential. We need to redeem public perception of nuclear, and advanced reactors need advanced research reactors. Just like current reactors had hundreds of research reactors around the world first before the current light water reactor became, widely used. And that's it. Well, there's, if you just search University of Illinois Microreactor project, you'll come with the project website. Nuclear News, that's our trade publication. That was our cover story on April 22. So if you search Nuclear News, University of Illinois Microreactor, that will come up with April 22 article. Connected to this, the Microreactor project is Illinois Microreactor R&D Center, which sits on top and does many projects related to microreactors. NRC, if you go to our website, there'll be links from the licensing page, there'll be links to NRC UIUC project website and to all the licensing, well, not the licensing, but all the pre-licensing documents submitted. And the contact info, I need not myself, but the director of the center, Ellen Brooks. But feel free to reach out to me, Tomasz Kozlowski. If you don't remember the name, search for NPR department, faculty, and look for the one with Polish name. Okay, it will be me. I think I'm the only one. Thank you. That's it. I'll take any questions that you might have.
Yep, so like I said, if you have a question and you're in the room, feel free to just raise your hand and say it. And then for our online audience, please put your questions in the chat.
Question here?
So you had mentioned that you don't want to go after low value products, namely electrons, but you still talked about electrons.
Yeah.
Is heat the high value product or hydrogen, or what is the high value product?
So actually, this is kind of separate, but we did fundamentally all power plants produce heat. And it's actually all the other things, electrons are a byproduct of the heat. You can think about it this way. So we definitely start with heat. And then what do you do with this heat? we had, it's not part of this, but separate analysis, if there was like something like 50, 20, 30 megawatt reactor, what would be the most profitable? I can tell you, electrons are the least profitable. Hydrogen is medium profitable, like actually a lot better and really profitable, and a little better would be ammonia production, is even more profitable from that heat. So, depending on the local, so this is the thing that is very much, and this is a little bit beyond this, very much market dependent and very much local conditions dependent. In Alaska and Hawaii, making electrons would make a lot of sense. In Illinois, putting it next to ammonia plant would make a lot of sense. In southern US with the data centers, it would make a lot of sense to put it with Amazon or Google, whatever data center. So again, it's conditions dependent. Okay? But in general, as a mass-produced electrons on the and again, these circumstances, they would have to be their own. But if it's like on a normal, MISO grid, then there's a bidding, MISO bidding, then there's almost no way that this would get to like single cent price per kilowatt.
So if heat is your primary product or your initial product, there's some target or expected cost per BTU.
Right.
What is that number?
Yeah, I can't tell you. I cannot tell you not because so here's also maybe a little bit is not answering directly, but something conceptual. First, as experimental reactor, it will be a lot more expensive than a final commercial product. There's no way around it, and I don't think we should pretend anymore. As a university research, do you think my research makes money? Show me science and engineering professors whose research make money. There are some, but is our research on quantum physics, our research on space shuttle materials, our research on supercomputers, our research on cancer treatments? There are thousands of it. Most of that, I would say, was a waste of money, in a sense that vast majority of drug therapies, cancer therapies, radiation therapies, whatever the quantum computers do not produce a product to sell. Right? So as a university, I think our job is to try kind of higher risk that ultimately might not produce a product to sell, but some of them will. Some of them will. And I think as far as the risk, this is one of the lowest risk things I can imagine. Versus going for a multi-billion quantum computer that I think will eventually get there, but do you think that customer will buy a quantum computer for millions of dollars? It has to get to $1,000 price, right? So in that sense, the same economies of scale have to take over, and it has to be mass produced at the factory, let's say on the order of tens or hundreds per year. Then I think in that case, yes, it will be economical and it will be beneficial. It will be just like any heavy industry, similar price. Okay. Does that answer the question?
I would still love to know what dollars, even if it's the far future condition, I'd love to know what dollars.
So I can tell you that so there is an easy answer because this is the target of many, not only I said it earlier. So the easy target is that all the microreactors, as far as electricity, target that they have to get like below somewhere around 40-50 cents per kilowatt hour in order to fit into that specific market.
Okay.
But they would not fit in the Illinois market where it's let's say less than 10 or less than 20 cents per kilowatt.
Okay, thanks.
Yeah. So that's where they have to get under that. Yeah.
Do you anticipate once you get through the demonstration phase and have a work to prototype that you are comfortable with, do you anticipate that something of this scale is usable in third world countries or supplying electricity, or is it too sophisticated for that?
In third world countries, you said?
Yeah.
So it is expected that it would be not the first one, or not this one, but it is expected that these things have to be at least semi-autonomously operated. That is the expectation, because you do need, like a dispersed, 100 of them more dispersed. So they have to be, you cannot have, 20 people crew at every location. But you can have, imagine, traveling 20 crew for maintenance. That's completely doable. That's how many industries operate. So benefit of this one is that it's not shown, or it's not clear on the side, that it is fully underground, and it is designed to be, if cooling was to be turned off, it can be cooled by internal, recirculation of just, heat. If you have something hot, the air will, rise it and cool it down. So it's intended for that. So if any event, it could be isolated from on the ground or at the ground level, and let it, and then deal with the situation if there is some dangerous or some situation where then you need a crew or some external help. Does that answer the question? Under IEA rules, the country without developed infrastructure would not be allowed to have a reactor under IEA rules. So we can think about several countries, whatever the examples, but their power grid has to be good enough, their road has to be good enough, their sea lanes, if they are like accessible, this will be accessible from sea, have to be good enough. Their education program has to be good enough, and actually that's good enough is pretty high standard. So again, and there's been like I say like those 3 or 4 obvious ones, but there's like a 20 if you search on IEA new nuclear country development program. There'll be like the top level goals, the milestones, at which point you demonstrate what capacity you have, and it won't be like that. The country just wants it, and somebody will start it. It's not like that. That's impossible. And not only that, Western countries would not allow it. IEA rules would also not allow it. So even if it was outside of, let's say, US whatever sphere of influence, I'm pretty sure that our other countries would not allow it. Yeah. And again, it would fall under IEA. So I can tell, like, what I'm more familiar with, Poland is going through actually that IEA process. And as far as infrastructure, as far as this kind of basic, the roads, electric grid, existing power plants, existing, roads or air roads and the sea roads, it's all well developed and capable enough. It's the education that is catching up, even with the education system of Poland, and as far as the non-nuclear education is perfectly fine, but there needs to be that component.
How does the microreactor compare with the kind of nuclear that's in a submarine?
Yeah, so that is, as far as power, my understanding, and I hope perhaps somebody can confirm with Wikipedia, is that the submarine reactors are like 20-30 megawatts. So as far as power, it's similar. Megawatt thermal, meaning that electric is about 1/3 of that, right? So for 10 or 5-10 megawatt electric. But submarine are much miniaturized versions of a pressurized water reactor. It's a PW. It's not gas-cooled reactor. Graphite moderate. It's like pressurized water reactor, which is pressurized water with UO2 fuel. The reason why light water reactors go 2 years with the refueling cycle versus submarines have this kind of 20-30 years without refueling is because they are allowed to go to high pressure. So in the end, again, kind of fundamental property is one fission creates fixed amount of energy. There's no way around it. So if you want more energy, you need more uranium. And so yes, they can generate more total power because their enrichment is higher. That would not be allowed in civilian purposes. And I imagine this is just my guess that it's something like 95-96% enrichment, but that's just my guess. Versus civilian is 20%. And again, that's under IEA rules.
So would you consider the nuclear sub, which generation would it be in, or is it?
That is like improved to Gen 2. Yeah, that is like a. Yeah, that is like a small version of pressurized water reactor. So maybe something like this. Yeah, they were developed to get actually submarine was first and then scaled up for a full PWR. Right, the recovery program, the nuclear program was the Seawolf and what's the other one? And Nautilus, right? The first nuclear, I don't know if they were submarines or the ships, surface ships, but one was like a pressurized water, one was like sodium cooled, and both of them were scaled for commercial. There's no commercial sodium, but they're commercial. For prototypes, to military, to civilian. Now we're trying to skip the military, although perhaps you know from the news, military has Army has a pellet project, so microreactor that's I think already contracted or already either with BWXT or with HTGR. Remember, I mean I'm sure it's in the news which one was the final selected design, and especially separately Army has a plan for Alaska for one of their bases, microreactor for the base, and their plan is for sodium cooled reactor. So you can kind of see the mirror of the past, that also the first two were sodium cooled and low water cooled for the submarine or for the surface ships. And now Army wants they have active project to build one for one of the military in Alaska. I believe they selected Oklahoma. Yeah, that will be either from Oklahoma or from Army.
So why wouldn't the military use this for remote bases? Because they don't, I mean, the cost of electricity at a remote base is very high, generally based on diesel fuel.
It makes a lot of sense. But let's say I'll point out this. Well, maybe I'll point out. Let's start with this. This is already kind of a good picture. I'm trying to find some nice picture to this. Oh, sorry, this one. If it's to be stationary, I think that makes a lot of sense, and I think they should do it. If it's the military, as Project Pellet actually have a concept that it would be transportable. I mean, not transportable just on a whim, but basically used for many years, then perhaps transported somewhere else for refueling, then used many years, then again so in that sense transportable. That's a tough one. And why is it that? Not that we cannot do it. Anybody seen EBR-1 reactor? Like it's a museum in Idaho. The reactor itself can be very small. Or Purdue reactor. Anybody seen Purdue reactor? That's where I worked on. It's like foot by foot by foot. The reactor can be very small. The problem is that you need a lot of shielding. So
what's that?
Shielding, radiation shielding. So in addition to this, reasonably small reactor that can generate a few megawatts, no problem. You would need 3 feet of concrete or water around, probably concrete. So at this point, it becomes a little awkward. Can you lift that? If this was full of concrete block, could you lift it? Yeah, but is that something that's easy? Probably not, right? Probably not that. I don't know what's the maximum load of their helicopter. I don't know what's the heaviest helicopter for the Army. Anybody knows how many tons? They can lift tanks, but I imagine that might be heavier than a tank. That's just my guess. But helicopters, right? The heaviest helicopters do lift tanks, which is I don't know, like 20 tons. I don't know. So,
Okay, so we are coming up on the hour mark. Are there any last questions? And Tomasz, do you have any final remarks that you want to leave us with before we end this seminar?
So I don't know the day or the time. Well, I know the time now, but the problem is that it changes every semester. So we do have open to the public meeting every first Tuesday of the month. Do you remember if it's at 10 or 11? Because the time changes.
It's been 11.
It's been 11, right? So it's 11 this semester, but it will change like next semester. But it's still, I'm pretty sure it's still going to be Tuesday in Talbot, in our new engineering building, in one of the rooms. We had it for more than a year. People come and ask questions, and we can discuss whatever you would like about the project or reactor, about nuclear power, about whether about either our campus situation or in general. about safety, about fuel, about licensing status. So it's Tuesdays, first Tuesday of the month. Right now it's 11 a.m. So the next one in December will be, what is now? No, now it will be the first Tuesday in November. Then there'll be one in December, but for next semester we'll change the time because our teaching time schedule changes. So then it will be adjusted a little to accommodate it.
Okay, great. Well, thank you so much. And for our attendees, we do have 2 more sustainability seminars happening in November. So you can find those on the ISTC website if you're interested in attending those. Thank you again, Tomasz.
Thank you for the